Hi everyone, we are continuing with polar area, but we're moving on to finding the area between two polar graphs. All right, so first problem we're given is r equals 3 sine of theta and r equals 2 minus sine of theta. So first thing I would probably want to do is draw a picture. So I know that this is going to be a circle with diameter 3 going up in the y direction because it's sine, so something like this, right? And then for this graph, I'm just going to go up 2, 1, 2, down 3, over 2, over 2, and I get sort of a cardioid looking graph. Okay, so what I want is the area inside of my circle. Okay, so I want this area, and I want to get rid of this area down here, which is our intersection. So essentially, so I need to think about what area I want and how to get rid of the area that I don't want. Okay, well, first thing I need to do every time I'm dealing with two functions in area is I need to find their intersection points. So I'm going to set these two equations equal to each other. Okay, I need to solve for theta because I need to know at what angle these are intersecting each other. So I'm going to add sine to both sides. That's a 4. And divide. So I get 1/2. That means that theta equals pi over 6 and 5 pi over 6. So I know that these are intersecting right here at pi over 6 and then over here at 5 pi over 6. Okay, that's where I'm intersecting. Well, so I want the area that's in the circle. All right, so it probably makes sense that I start with that. Okay, so I want the area in the circle. I want to get rid of the area that is inside of my other shape here, like my cardioid here, right? So it would make sense to start with the area of my circle and then subtract the area that I do not want. So I'm going to set up my area. Okay, so similar to the notes that we did yesterday with our rows problem, I'm actually going to find the area of half of my circle and multiply it by 2. And the reason why I'm going to do that is going to become a little bit more apparent in the next problem. But I think it's going to be a good habit to develop. So I'm actually going to find, again, the area of half and then multiply it by 2. So I'm going to multiply it by 2. Right, so the area is 1/2 integral. I know they intersect at pi over 6, so that's where I'm going to start. And I'm only going halfway, so I'm actually going to stop this at pi over 2. Okay, so from pi over 6 to pi over 2 of r squared, so 9 sine squared theta. Right, so this is the area of my circle that I want. It's actually the area of the whole circle. Now I need to subtract the area that I do not want, which is part of my other shape. So I need to represent that area with another 1/2 integral. I'm going from pi over 6 to pi over 2 of my radius, so 2 minus sine of theta squared d theta, close parentheses. Okay, so again, it would have been the exact same thing if you didn't multiply by 2 and went from pi over 6 to 5 pi over 6. But in the next example, it kind of shows you why it's easier to do it this way if you kind of have weird angles. So let's move on. Okay, so similar problem. I want to find this time the area that they have in common between my two functions here. So I have a cardioid and I have another circle. So let's draw a picture. This time I'm going 3 in the x direction. So here's my circle, right? And I have a cardioid going 2 out, 1 up, 1 down, like this, and then my heart. Okay. So here's my cardioid, here's my circle, and I want the common interior. So I want all the points that they have in common here. Well, again, the first thing I need to do is set these equal to each other to figure out where they intersect. So I subtract cosine from both sides, I divide. So I want to know where cosine is 1/2, which is at pi over 3, and 5 pi over 3. Right, so I know they intersect like right here, and I know they intersect right here. right? So it'd be kind of hard to see, but the area that they have in common is encompassed in my cardioid here, and also a little bit is outside the cardioid, or a little bit is outside this area here in the circle. Okay, so what I'm going to do is, again, set up my area equation as if I'm taking just half of it. So I'm just going to focus on this top half here. The reason why I'm doing that is because if I do my integral from pi over 3 to 5 pi over 3, it's going to integrate all of this. Okay, all of this area, and I don't want that area, I want this area right here. And so the reason why it's easier to just do half is because you don't really have to worry about what direction you're integrating in. So normally I would be integrating kind of in a counterclockwise direction. If I'm going from pi over 3 to 5 pi over 3, I don't really want to worry about that. And so it's going to be much easier to just go from 0 to pi over 3, which gives me half, and then multiply it by 2. Again, if I go from pi over 3 to 5 pi over 3, that's going to integrate all of this stuff over here, which is the exact opposite of what I want. Okay, so it's much easier to not have to worry about any of that and just find half of it, multiply it by 2. It's the same thing with the rose petals. So I'm going to multiply by 2 and set up my two area equations. So 1/2 integral, I'm going from 0 to pi over 3 of, we'll do my cardioid first, so 1 plus cosine theta squared d theta plus, all right, and so like I said before, most of my area is contained in my cardioid here, but a little bit of the circle is left over after they intersect, which is still inside the cardioid. And so I have to take into account that area as well. And so that's going from pi over 3 to pi over 2. Okay, and that is my circle. Right, so again, this is the area of my cardioid. It goes from 0 to pi over 3 where they intersect. Right, so it's just half of my cardioid. And then there's a little sliver of area over here, which is contained by my circle. And so that goes from where they intersect, pi over 3, until pi over 2, where my circle essentially ends in half there. Okay, and again, I'm just doing half of it because I don't want to worry about what happens when I integrate the whole thing, okay, like what direction I'm integrating in, so it won't give me the wrong area. Okay, well, that is it for these notes. I'll see y'all later.